Hello, hello. Today we are going to finish up talking about the conditions in order to use regression inference, and the acronym we're using is LINER. This is section 12.1. We discussed them in class today, and then today we're going to, in our video, look at a specific example of students and which row they sit in, and then their score. So the first thing that I need you to do is in your calculator, enter your data, right? The row is going to go in list 1, and the score is going to go in list 2. So it looks like this. So since there were 4 scores in row 1, you can see that there are 4 ones, and then the 4 scores. So pause this video to do that. Once you have done that, we're going to go through our conditions. The first condition is linear. So we need to look at the scatter plot to check that the overall pattern is roughly linear. We had a picture of the scatter plot on our example page today, but say you didn't. Okay, so you'd have to make a scatter plot. The best way to make a scatter plot is in your calculator. So just a refresher on how we do that. You would need to go to your y equals, and I already have my equation there, but I'll clear that out to show you. So I'm going to go to my plot and make sure my plot is on, and it should be a scatter plot. My x should be my L1, my y should be my L2, and then when I go to zoom, clear out of that, sorry, go to zoom, and we want to go to zoom 9, which is the zoom stat. Then there's our scatter plot. So we can say that our scatter plot shows a weak linear relationship. Okay, that's the first thing we could say. Scatter plot shows a weak linear relationship. In addition to checking the scatter plot, it says up here, look for curved patterns in the residual plot. So now we need to remember how we create a residual plot. Okay, check to see that the residuals center on the residual equals 0 line at each x value in the residual plot. So the residual is the difference between the actual value and the predicted value. So we need to calculate those. So what we're going to do is we're going to go clear out of that, and in calc, I'm going to go to step number 8, and that's my linreg. That gives me my least squares regression line. X's are in list 1, Y's are in list 2. I'm going to store it in my Y1. So how do I get there? I'm going to go to vars, go over to yvars, function, and pick Y1. So now when I do this and I hit calculate, there's my equation right there, but then I go back to my y equals, and my equation is stored. So if then you went to graph it, you would see your line of best fit appearing on your graph. Now we did that in order to find our residuals. So I'm going to go back to stat and edit. And in list 3, I'm going to calculate my residuals. Residual is the actual, which our actual y values are in list 2, minus our predicted. How do you find the predicted? You plug in the x values to your prediction equation. Our x values are in list 1. Our prediction equation is stored in y1. So I'm going to pick y1 and substitute in L1. So I'm putting all of the x values into my least squares regression line, and then subtracting the difference between the observed and your expected. So you'll get some positives, some negatives. List 3 is now containing my residuals. So now I need to look at the residual plot. So I'm going to go back to stat plot. And now instead of graphing list 1 and list 2, I'm going to graph list 1 and list 3, because list 3 is where my residuals are. So now, clear out of that, I'm going to turn my line of best fit off just for a minute. And now go back to my zoom, and there is my residual plot. Now the residual plot does not show any obvious leftover patterns. So there's no curved patterns there, right? It's pretty evenly spread out. So that's what we can say. So we can say that the residual plot does not show any obvious leftover patterns. Another way of saying that is that there's random scatter about the line, about the residual equals 0 line. Next condition to check is independent. Look at how the data were produced. Random sampling and or random assignment help ensure independence. This was an experiment, so there was random assignment. So we can say students were randomly assigned and were also monitored for cheating, so that knowing a score for one student should give no additional information about another student's score. We don't need to do the 10% condition because we did not sample. Students were randomly assigned to seats and were monitored for cheating, so knowing the score of one student should give no additional information about another student's score. Now, the next one we want to do is to make a stem plot, histogram, or normal probability plot of the residuals to check for skewness or other major departures from normality. So it's really up to you what you want to do here. I'll show you how to make the histogram of the residuals. Okay? So what I'm going to do in my calculator, because I have my residuals in list 3 right now, right? I'm going to go up to my plots, and I'm going to change it to a histogram. And I'm going to do a histogram of my residuals, which are located in my 3rd list. And that's okay. So now when I go to Zoom Stat, this is a histogram of my residuals. So it appears kind of symmetric. I wish there's a better way to do this so that you change the scale here. I could have also done a normal probability plot, which I'll also show you here in a moment. So, a different way of doing this, so this is a wider bin width, if you will. I'm going to show you another one. So, right here, this is another histogram of the residuals. And this down here is the normal probability plot. We learned about that back in chapter 2, I think. It graphs your residuals against your other. So up here it did your x's versus your residuals. This one is different. So by looking at those, we can see that it seems okay. Histogram is, roughly symmetric, unimodal. Normal probability plot is roughly linear, so normal conditions should have been met. So we have, I'll cover this so it goes for the other one. So here's my normal. Our next one is equal variance. So again, look at the scatter of the residuals, which we already looked at. Back up here in our linear condition, we looked at the scatter of the residuals, the residual plot. The amount of scatter should be roughly the same for the smallest to the largest x value. So let's look real quick again at our residual one. So I'll just switch this up again. So go back to this guy, list 1, list 3. And we can see there is a different amount of variability within each row, right? This row right here has a lot of variability. This row right here, not a whole bunch. The differences aren't very large though, and it doesn't seem as though there's a systematic pattern, such as, it's increasing or decreasing from one way to the other. So we can say it's alright with equal variance. So like I said, although there is a different amount of variability in each row, the differences aren't very large, and there is no systematic pattern, such as increasing variability as x increases. It's a random pattern, which is what we want to see. The last condition of our liner that we have to check is random. We need to see if it was produced by random sampling or a randomized experiment. In this case, the students were randomly assigned to seats. So students were assigned to seats at random. Our conditions probably take the longest of all the things that we need to do once we're going to start our 4-step process here, when we get to confidence intervals as well as significance testing. We need to go through all of these. If something isn't met, address it, but maybe also still continue if it's a problem saying, oh, do the confidence interval for the slope. Chances are you want to continue. Okay? So, the back of your notes is just talking a little bit more about standard error of the slope. I broke this down for you in class. S is the standard deviation of the residuals. That's given by this formula right here. Okay? So, and like I said, you're never really going to have to calculate this. You'll probably only have to interpret it. Okay? So, if you're wondering how the heck do you interpret the standard error, it talks about how far away the true slope is on average from the estimated slope. So if we were to repeat whatever many times, the slope of the estimated residual line would typically vary by about, insert standard error here, from the slope of the true regression line for whatever context we're dealing with. Okay? So when it comes to this, we're not going to be using it as far as this formula or this formula. These are on your formula sheet should you need them. But like I said, you probably won't use it. You'll most likely find your standard error from your computer output. Okay? Now, the two inference techniques that we're going to be using for slope are confidence intervals. We're going to be using T intervals. And then significance testing. So we're going to be using T. Just like when we use for T for means, we're going to be using T for slope. Right? Our formula is still generally the same. It's your statistic, right? Plus or minus your critical value times your standard error. Okay? Degrees of freedom is going to be n minus 2. That is a newer thing here. Okay? When we're doing our significance testing, we're hypothesizing that our true value, our beta, our true slope, is whatever they're hypothesizing. Computing our test statistic, right? Actual minus predicted over our standard error. Again, degrees of freedom is n minus 2, and we're calculating T statistic using then our p-value to come to our conclusion. Okay? So tomorrow in class, we're going to do our first example. Okay? And if you'll notice on that next page, I'll show you some of it, they give us our computer output. So that's going to help us when we construct our interval. Okay? All right. Have a good night, guys.